So let's talk about this. So product rule. There's lots of ways to write it. One way of writing it is that the derivative of f times g is f prime g plus f times g prime. There's lots of, but like you write it as f prime of x times g of x plus f of x times g prime of x. You can also change the order, right? You write it as f prime g plus g prime f. Really, there's lots of ways you can write this. Let's put this over here. And then the example of this could be something like finding the derivative of x cubed times sine of x. So the derivative of x cubed times sine of x would be 3x squared times sine of x plus x cubed times the derivative of sine, which is cosine of x. There's a product rule example, but you might have made up something else or not at all. Totally fine. Same kind of, actually, and so what I would point out is the quotient rule and the product rule actually have a lot in common with each other. The quotient rule, at least the top part of the quotient rule, looks almost identical to the product rule, except for the minus sign. So the derivative of f over g, or you might think of it as high over low, is f prime times g minus f times g prime all over g squared. Although the words I actually say in my head are, watch me point and watch me say. So I say the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. So when I actually write out a quotient rule problem, I usually don't write f prime times g. I usually write g times f prime, and I actually write the things out. Let me show you what I mean. Let's say I'm trying to write something that will fit in here. Let's say that I wanted to take the derivative of, let's see, something that will fit that's not too terrible. Sure, let's say we had tangent of x over x squared plus 1. Plus, if I was actually finding the derivative, I wouldn't do the derivative tangent times x squared plus 1. I would write x squared plus 1 times the derivative tangent, just because that's the way I hear it in my head. And it's also fine to multiply in either order. So it's okay if we do x squared plus 1 times the derivative tangent or the derivative tangent times x squared plus 1. So I'm going to write this as, hopefully I can fit this in here. The bottom, x squared plus 1 times the derivative of the top, which is the derivative tangent, which is secant squared of x. It's going to be close. Minus the top, tangent of x, times the derivative of the bottom, which is 2x, all over the bottom squared, which is x squared plus 1 squared. And finally, the chain rule, again, this is the way I would write it. I'm taking the derivative of a composition of functions, f of g of x. And the way I'm going to write the derivative is going to be f prime of g of x times the derivative of the inside, g prime of x. Or as I like to say it, I'm thinking of it as the derivative of the outside, leave the inside stuff alone, and then multiply by the derivative of the inside stuff. Often you will hear me say the words, right? If I'm taking the derivative, say, I'm gonna write it slightly differently. I'm not gonna write anything specific. If I was taking the derivative of f of some stuff, the derivative would be f prime of my stuff. So the derivative of the outside, leave the inside stuff alone, and then we multiply by the derivative of the inside stuff always. So if I was going to pick an example here, I might pick something like, I don't know, x to the 6th plus cosine of x to the 9th power. If I take, and instead of writing a prime for the derivative, I'm going to write a d dx in front, because that's also a way of writing take the derivative of something. So the derivative of some stuff to the 9th power. So what I like to say is I know that the derivative of x to the 9th is 9 times x to the 8th. So the derivative of some stuff to the 9th is 9 times my stuff left alone, unadulterated, to the 8th power. But then I have to multiply by the derivative of the inside stuff. I'm going to multiply by 6x to the 5th plus the derivative of cosine is negative sine. So instead of writing plus negative sine of x, we're going to write minus sine of x. So some examples of those rules in action. As always, you're welcome to ask questions along the way. If you want me to explain something more in depth, please just say so. All right. Also, since there's only 4 of you here, I know Priscilla's name, and it was Arthma. And what's your name? Caitlin and Caroline. Cool. All right. Try to remember those. So let's look at some log rules. So the log, interesting. All right. So I know why these are written in this order, because this is typically the order that if you were trying to use integration by parts, you would pick your u equal to a logarithm if you had one, an algebra term if you didn't have a log, a trig if you had neither of those, and almost never an exponential. But that's why these are written in this order, even though that's probably not the order I would teach the derivatives in. Well, let's go with it. So derivative of natural log of x, 1 over x. Derivative of log of x. So remember, log of x is really log base what? Not e. Natural log of x is log base e. Log of x is log base 10. One way you could, one thing I just thought that maybe you could, it might help you remember, it might not, is log, the L and the O kind of look like a 10. Whereas natural log, there isn't an L and an O, so it doesn't look, I don't know, that's not maybe the best ever, but it may work. So this is going to be 1 over, so the rule for differentiating a log with a different base is it's 1 over x, and then you also have to have the natural log of whatever the base is in the denominator. We can talk a little bit more about that in a second if you would like to, but let's finish off this part here before we do that. So here, the derivative of log base b of x, so instead of having log base 10, I have log base b, so it should be the same pattern. You all should write down it's going to be 1 over x times something. Not natural log of 10, but what? Yeah, x times natural log of b. There's a couple ways you could justify this to yourself, and I feel like you all might want some justification here. So let's talk about it for 1 minute here. So expanding on that for just a second, if I was going to find, let's start over here, the derivative of log base 3 of x. I know the answer should be 1 over x times the natural log of 3. But I'm going to show another step here. So there's actually 2 different ways you could solve this. One way is to use what's called the change of base formula. So the change of base formula says that we can write the log base b of x as the log, pick any base you like. I'm going to write a for being very general, of x over the log base a of b. That's the change of base formula. And it can be derived. It's not terrible to derive, but we don't have to do that unless you want to do that. One example I like to write is the following. So let's say I wanted to find, sure, let's make it fun. Let's say I want to find log base 4 of 8. So we're asking the question 4 raised to what power equals 8? Well, it's not 2, because 4 squared is equal to 4 times 4, which is 16. And it's not 1, because 4 to the first is 4, which is, right, not 8. It's something between 1 and 2. One way you could do this, here's the long way of doing it, is say, well, let's set it equal to x. Let's rewrite this as an exponential equation. What's my base? What is my base? What's my power? Not 8. It's x, and it's all equal to 8. So these 2 equations are equivalent. And then I can rewrite this right-hand side both as powers of the common base 2. I can write 4 as 2 squared to the x. I can write 8 as 2 to the third. So then I can rewrite this equation. Well, 2 squared to the x is 2 to the 2x, and 2 to the third, still 2 to the third. And the whole point here is that if you can rewrite both sides as powers of the same base, those powers have to be equal to each other. So 2x has to equal 3, which means x is equal to 3 halves. So in other words, log base 4 of 8 is equal to 3 halves. you might be asking, what does this have to do with the change of base formula? Well, another way you could have done this is said log base 4 of 8 is equal to, I'm going to use the change of base formula. What base might I want to pick here if my numbers are 8 and 4? Maybe 2. So I'm going to write this as, so right here's my formula up here. Instead of writing log base 4 of 8, I'm going to write log base 2 of 8 over log base 2 of 4. But these are things we actually know how to figure out. I'll remind you, in case you've forgotten, when I say log base 2 of 8, what I really mean is 2 raised to what power gives us 8? Let me ask you, 2 to what power equals 8? It is 3. Because 2 times 2 times 2 equals 8. Now, this bottom one's a little maybe confusing because 2 times 2 equals 4 is just weird. It's weird. I mean, it's not weird. It's an anomaly because 2 times 2 equals 4 and 2 plus 2 also equals 4. And so it leads to some weird kind of coincidences in math. So I want to point out that log base 2 of 4 is equal to 2, not because 2 times 2 equals 4, although yes, actually it is. It's because 2 to the second power is equal to 4. So just be careful there. It can be a little, right? Log base 2 of 8 doesn't equal 4. Right, log base, because 2 times 4 is 8. Log base 2 of 8 equals 3 because 2 to the third power is equal to 8. But look, those are the same. So that's an example of how the change of base formula actually works. But then what we can do is we can say, well, log base 3 of x, the base I would really like to have is the base e, the natural base. So I could totally rewrite this as the derivative of the log base e of x over the log base e of 3. But nobody writes log base e. I should write this as the derivative of the natural log of x over the natural log of 3. And here's something that's useful to know. I shouldn't use the quotient rule because my denominator is just a constant. So I should really actually think of this as the derivative of the constant 1 over natural log of 3 times the function natural log of x. When you take the derivative of a constant times a function, what does the constant do? What do I like to say it does? You might not have heard me say this, but I like to say well, this is true for derivatives and antiderivatives. Constants like to hang out. Constant multiples like to hang out. If it was a constant by itself, what's the derivative of a constant by itself? 0. But if it's a constant times a function, that constant likes to hang out, and we get the constant hanging out, and then the derivative of the natural log of x is 1 over x. Oh, look, we're getting 1 over x times the natural log of the base. So that's why this formula works the way it does. Cool. That's why here the derivative of log base b of x is 1 over x natural log of b. All right, so that's the logs. Move along to the algebras. So the derivative of 5. We just talked about this. What's the derivative of 5? Yeah. Derivative of constant is 0. What's the derivative of x? 1. And actually, let me ask a quick one here. What's the derivative of 6x? 6. Derivative of x to the n, power rule. You're going to get n times x to the right. And that's true for any value n. It would technically even work if n was 1 or n was 0, although we don't typically use the power rule. We know the derivative of x to the first is 1, and the x to the 0 is 1, so it's derivative of 0. Yeah.
So is that why like times, x to the second power plus 1? Is that why?
There's more to say.
2 plus 1?
Right, exactly, because you're reversing this. That's exactly why the antiderivative of power is the anti-power rule, and it undoes what the power rule does. Well, because so the thing is, when you're trying to undo an operation that something else has done, you have to reverse the things in the reverse order. So here, when you do the power rule, when you do the derivative of x to the n, you first multiply by n and then you reduce the power. Whereas to do the anti-power rule, you're going to undo those things in the opposite order. So first you're going to increase the power because you're undoing the reducing of the power. And then after that, you're going to divide to undo the multiplication by the new power. So it's exactly the opposite steps in the opposite order. Derivative of 1 over x, I would definitely rewrite that as the derivative of x to the negative first, which is then going to be -1 times x to the negative second. I don't usually leave it like that. I usually like to rewrite that as -1 over x squared. But either way of writing it is technically correct and fine. I like writing this because it's more clear to me writing it this way, that 0 is not in the domain of this expression. So this function you could say is not differentiable at 0. It's also not defined at 0. You look like you have a question.
Or I mean, ln of x, sorry.
That would be the antiderivative. Right, so certainly the derivative of natural log of x is 1 over x. So the antiderivative of 1 over x is natural log of x. For any, no, that's a good question. Thank you for asking it. Lots of people make the mistake when they're using integration by parts of saying the function u is 1 over x and the derivative is natural log. The derivative is -1 over x squared. The antiderivative is natural log of x. Similarly, people make the mistake of saying that the antiderivative of natural log of x is 1 over x. That's not true. The derivative of natural log of x is 1 over x. The antiderivative of natural log of x is something else entirely that we actually need integration by parts to find. We might do that at the end of the day because it is worthwhile. I can see Dr. Zadell asking it on an exam. Similarly here, it pays to rewrite this as the derivative of x to the 1/2 and then use the power rule and get 1/2 times x to the -1/2. Again, this is a cool, fine way of writing it, but I often like to rewrite this as 1 over 2 times x to the positive 1/2, or even as 1 over 2 times the square root of x. I find those very useful ways to write it, especially when I'm doing a u sub. Because if I rewrite it this way, it's a little more obvious to me that root x is kind of the thing I chose for you in the first place. Finally, derivative of x over 5. Again, we have something that looks like a quotient where we shouldn't use the quotient rule. If your denominator is a constant, or I should just say this, if you're dividing by 5, you're really multiplying by a constant. Dividing by 5 is the same as multiplying by what? Exactly. So we should really imagine this as being the derivative of 1/5 times x, and that's just going to be 1/5 times 1. Just 1/5. More generally, if you were taking the derivative of something like x cubed over 7, yeah, you could write it as 1/7 times x cubed and then say the derivative is 1/7 times 3x squared. Or you could just say, I know dividing by 7 is just really multiplying by a constant. I can just take the derivative of x cubed and get 3x squared over 7. That is a totally valid thing to do. We're just taking a shortcut, really. All right, that's most of the, there are other algebraic things too. Like you could have funkier powers, or you could have to simplify things with powers. But this is kind of the idea of algebraic terms are really just x to some sort of power. And so when I say I'm doing a u sub and I'm looking for an algebraic term, or as I say, any power of x, I am looking for something like this. All right, let's talk about the trig ones. So the trig ones, definitely need to memorize them because all these antiderivatives definitely come up. So the derivative of sine of x is cosine of x. And the derivative of cosine of x is negative sine of x. The derivative of tangent of x is secant squared of x. And there's a pattern here. The derivative of cotangent of x is cosecant squared of x with a negative sign in front. So it's negative cosecant squared of x. What I'm really thinking about doing here is that tangent is with secant squared and cotangent is with cosecant squared. I'm just putting the co prefix on both of them. And then every co-function, cosine, cotangent, and cosecant, has a negative derivative. So here, I'm just going to put a negative sign there and see what I get in a minute. Derivative of secant of x is secant of x times tangent of x. So now I'm going to put cos on all those functions, and the derivative of cosecant of x is going to be negative cosecant of x times cotangent of x. Definitely worth memorizing. I guess you don't need to know this, but since it's on the list, the derivative of the inverse sine is 1 over the square root of 1 minus x squared. You probably don't need to know that, but there it is. And the derivative of inverse tangent is 1 over 1 plus x squared. I like to write it as 1 plus x squared. Other people might write it as x squared plus 1. It doesn't matter, right? The order of addition doesn't matter. You can totally write that as 1 over x squared plus 1. Either way is totally fine. You are probably going to see some of this when you do some partial fractions problems. And then lastly, exponential functions. So the derivative of e to the x is, and the derivative of 5 to the x is, so yes, exactly. So what I want to point out here is logs and exponentials have a lot in common. They're very related to each other. They're literally inverse functions of each other. So for the logarithms, when you have a different base, we end up dividing by the natural log of that different base. For an exponential function, when you have a different base, you end up multiplying by the natural log of that different base. And again, we could make a similar-ish argument for why we do that. There's a lot. You could actually do some implicit differentiation stuff, or you could rewrite 5. In fact, let me actually rewrite that because I do think it's worth seeing just to kind of make sure that everyone believes what's going on here. I could totally rewrite the derivative of 5 to the x as, hold your hats. Hold on to your hats. Hold on to your hats is the way you should say it. Not hold your hats. Hold on to your hats. I was trying to like make, I think I was mixing together like hold your horses and hold on to your hats, and it's not that good. I'm going to write 5 to the x as e to the natural log of 5 to the x. And then the x gets to come down in front of the natural log of 5. So I can rewrite this as the derivative of e to the x times natural log of 5. Or as I am thinking of it in my head, the derivative of e to the stuff. And I know that the derivative of e to the x is e to the x. And so the chain rule version is going to be the derivative of e to the stuff is going to equal e to the stuff times the what of the stuff? The derivative of the stuff, which is exactly the natural log of 5. Because what we have here is x times a constant, and the derivative of x times the constant hangs out, and the derivative of x is just 1. So you get 1 times natural log of 5. Or rewriting this, check this out for a second. I want everybody to see that this part I'm putting in the box right here is the same as that, is the same as that, is the same as that. So e to the x natural log of 5 is really just our 5 to the x. So we can totally rewrite this as 5 to the x times the natural log of 5, just like we said it should be. Cool. So those are kind of I would say, the basic derivative rules we should all be aware of. And then you have to kind of be able to put it all together. So let's talk about a few examples of putting these rules together in these rules together in conjunction with the product, quotient, and chain rule. Because that's kind of where they're going to show up. Maybe less so the quotient rule, to be perfectly honest. The quotient rule probably isn't a big player in 17B, but certainly the quotient and the product and the chain rule do show up quite often. So let's look at a few examples. And I would honestly say probably the chain rule is the one that's probably the most important. So for any of these logarithmic, algebraic, trigonometric, or exponential functions, we should be able to find derivatives of the chain rule versions of this. So every time I'm doing this, all I'm imagining is the original function version, and I'm replacing the variable x with the word stuff. And every time I do that, I know I have to multiply at the end of the day by the what of the stuff? The derivative of the stuff. That's why I say the word stuff, because as soon as I say the word stuff, I know at the end of the day, I have to multiply by the derivative of the stuff. every time. So for example, if I was trying to find the derivative of, say, and I guess we should start with the log ones, because let's just follow the same order. The natural log of x cubed plus 5x. So what I'm really saying in my head is the derivative of the natural log of x is 1 over x. So the derivative of the natural log of some stuff is 1 over the stuff. But then, what do we have to multiply by? You're going to see the derivative of the stuff like 1,000 times. It's always the derivative of the stuff. So we're going to multiply by 3x squared plus 5. Yes, you could write this as 3x squared plus 5 over x cubed plus 5x. No, we don't really care. Except that I will point out that later on, I am going to rewrite this just so you can see something. So I want to point out that later on, if you had to anti-differentiate this function, you would let u equal the denominator with a u substitution, and then your du would exactly be the top. So in fact, we might as well. So let's just say, for example, if I was trying to integrate 3x squared plus 5 over x cubed plus 5x dx, we're going to let u equal the bottom. And we're going to be really happy about that because our du is exactly 3x squared plus 5 times dx. That's like an ideal situation. Because now I can rewrite my integral as the integral of, well, 3x squared plus 5 times dx is exactly my du. I'm going to get du divided by u. For some reason, people don't love writing their integrals this way. They really would like du to be at the end. So you are welcome to rewrite this as the integral of 1 over u times du, if that feels more comfortable. But either way, whether you're integrating 1 over u du or du over u, what's the antiderivative of 1 over u? This is something first. The natural log, and yes, we do need an absolute value here for domain reasons. So it's the natural log of the absolute value of u plus c. And then we plug back in what u is equal to, and we get the natural log of x cubed plus 5x plus c. Essentially, the same function we started with, right? There's a slight difference here because of the absolute value, but it's not something that's really that noteworthy. So I will also emphasize here, when you're doing a u substitution, you are literally undoing the chain rule. You are finding the choice for u is your stuff, right? My stuff was x cubed plus 5x. And then I was really hoping that the derivative of my stuff was also in my integral. That's why we make u substitutions the way we do. Let's look at some more examples. Let's say we wanted to find the derivative of the log base 2 of e to the 3x plus sine of 6x. This one's going to be a little bit gnarly. So I'm going to really ignore the 2 until the very end, because I know that that 2 means I'm going to have to, at the very end, have what in my denominator. And we look back at the list. See, when I had a log base b here, I ended up with a natural log of b in my denominator. So I know here I'm going to have a natural log of 2 in my number. You can even start off that way if you really wanted to. You say, well, I know I'm going to get a 1 over natural log of 2. It's kind of weird to start that way, but it's also totally fine. So I'm really ignoring the 2. Then I'm just going to say, what's the derivative of log of some stuff? Well, once again, it's 1 over all the stuff. And then we have to multiply by, I want you all to say it. Thank you. I don't think that was everybody, but I'll take it. The derivative, okay, what's the derivative? Ooh, we have an extra chain rule in this here. What's the derivative of e to the 3x? Times 3, right? Because now you've got an e to a new stuff. And the derivative of e to the new stuff is e to the new stuff times the derivative of the new stuff. So it's exactly e to the 3x times 3. Same deal for sine of 6x. Sine of 6x is sine of some different new stuff. And the derivative of sine of some different new stuff is cosine of your different new stuff times The derivative of that different new stuff.
One over the, yeah. Why did you write it as one over?
So here's what I'm doing. I'm using the fact that I know that the derivative of the natural log of some function of x. Well, what's the derivative of the natural log of x? Nope, stop right there. Just for the all right, you're doing base 2, right?
Oh.
But so if I just do the natural log of x, the derivative is just 1 over x. And you're totally right. And I should actually, so I will point out the derivative of the natural log of f of x is 1 over my stuff. What do I have to multiply by? Right. And I should say, if I have a different base is 2, the derivative of log base 2 of some stuff is going to be 1 over my stuff. I also have a natural log of 2 down there, but then I still said the word stuff, so I know I have to multiply by the derivative of stuff. And that's what's happening here. I'm getting exactly 1 over my stuff, e to the 3x plus sinus 6x, times the derivative of that stuff, and then also I have a 1 over natural log of 2. So here's my stuff. Here's the derivative of my stuff. Yeah. So let's talk about some algebra ones. Make sure I keep, let's make sure I keep things in order here. So I will say the algebra ones are maybe less so, like you can certainly throw stuff together or just some chain rule things. So let's look at a couple of examples. Like let's say, for example, I want to find, and I guess I'm trying to number things here. Yeah. I want to find the derivative. I'm going to use a different variable just to change it up. Let's say dy of y cubed plus tangent of y all raised to the 16th power. So the way I'm looking at this, and I'm looking for a lot of chain rule things here, but I'm looking at this as some stuff raised to the 16th power. Great. So I know that the derivative of x to the 16th power is 16 times x to the 15th power. So now my stuff gets to play the role of x. So instead of having the derivative of x to the 16th, I'm going to get the derivative of stuff to the 16th and get 16 times my stuff to the 15th power. What do I need to multiply by? The derivative of the stuff. So that's going to be 3y squared plus the derivative tangent of y is secant squared of y. Or we might have something where we can avoid using the quotient rule, like taking the derivative of, say, 2x to the 7th plus 5x to the 4th minus the square root of x plus 1 all over x cubed. Yes, you could use the quotient rule. But if you see a quotient like this and the denominator has only one term, not added to other things, it'd be totally fine if it, in fact, let's make it a 4x cubed in the bottom, just to make it a little bit different. You still only have a single term in the denominator because there's only one thing not added to other or subtracted to other things. And if this is the case, you should totally rewrite it. There's two schools of thought in how you do this. One way to do this is to rewrite it as the derivative of each thing divided by 4x cubed. So I've got 2x to the 7th divided by 4x cubed plus 5x to the 4th divided by 4x cubed minus, instead of writing the square root of x, let's write x to the 1/2 divided by 4x cubed plus 1 divided by 4x cubed. Or the other school of thought is to say, I'm going to have that entire numerator 2x to the 7th plus 5x to the 4th minus x to the 1/2 plus 1 multiplied by x to the negative 3rd, still divided by 4 though, right? That 4 does not get to travel up to the numerator. You could say, instead of dividing by 4, you could say times 1/4 if you want. And that is the same. So now, either way you slice it, bless you, you're going to get, let's see, let's look at it both ways. So I do 2x to the 7th divided by 4x cubed. X to the 7th divided by x to the 3rd is x to the 4th. And 2 divided by 4 reduces to 1/2. So I have the derivative of 1/2 times x to the 4th. 5/4 doesn't reduce, so I'm just going to write it as 5/4. And x to the 4th divided by x to the 3rd is x to the 1st. Here, the 1/4 out in front, I'm just going to have, so I'm going to have a minus 1/4. And x to the 1/2 divided by x to the 3rd, ugh. So I have to do the 1/2 power minus 3, and 1/2 minus 6/2 is negative 5/2. I get x to the negative 5/2. Finally, the last one here is going to be, now again, be careful here, 1/4x cubed, the 4 doesn't get to come up to the top. I'm going to write that as 1/4 times x to the negative 3rd. Or I could have gotten to the same place looking at it this way and saying, if I distribute this x to the negative 3rd times 1/4 to each term, x to the 7th times x to the negative 3rd is x to the 4th. And 2 times 1/4 is 1/2. X to the negative 3rd times x to the 4th is x to the 1. And 5 times 1/4 is 5/4. And so on and so on and so on. Same thing. I like doing it this first way personally. Second way is also totally fine though. Do be careful. I've seen people rewrite this as like the top 2x to the 7th plus 5x to the 4th minus square root of x plus 1 minus 4x to the 3rd or something like that. That is not correct. And then we're going to take the derivative just by using the power rule. We've written all these things as x to a power. We can take the derivatives using the power rule. So we're going to get, now let me write it this way. I'm going to think of all these constants just hanging out in front. So I'm going to get 1/2 times 4x cubed plus 5/4 times the derivative of x is 1 minus 1/4 times the derivative of x to the negative 5/2 is negative 5/2 times x to the negative 5/2 minus 1 is negative 5/2 minus 2/2, which is negative 7/2. And finally, plus 1/4 times negative 3 times x to the negative 3 minus 1 is negative 4. And then if we cared to simplify, we could. 1/2 times 4 is 2. 5/4. 1/4 times 5/2 is, it's actually a negative 1/4 times the negative 5/2 is a positive 5/8 times x to the negative 7/2. And finally, a 1/4 times negative 3 is a negative 3/4 times x to the negative 4th. And really, the reason I mentioned this example specifically is because you would also anti-differentiate this function in very much the same way. You would multiply it out until you had a bunch of different terms, and then you would just take the antiderivative of each of these terms using the anti-power rule. All right. What else do I want to say there? Sure. Let's do something like that. Yeah. So let's say I want to find numbers, James, numbers. Number 5. I don't know why I'm writing find here. Let's find the derivative of x to the 7th times the natural log of x cubed plus 2. So we're using the rules we've got, but also we need to use the product rule because I said times, or because there is a I mean, it's because of the product, not because I said time, but you know. So using the product rule, you don't have to write anything down, but you can think of like this is your f and this is your g, or this is your u and this is your v if you like to use those letters better. We know we're going to get the derivative of x to the 7th, and you can, if you feel like taking the derivatives in the first step is more work than you want to do, you can say, well, it's going to be excuse me, the derivative of the first thing, I like to write x to the 7th prime times the not derivative of the second thing. Plus, then we switch it up. We leave the first thing alone. And we multiply by the derivative of the second thing. The derivative of the natural log of x cubed plus 2. I don't like to write this intermediate step because it just takes too much time and too much writing. But you are certainly welcome to write this if it helps you kind of organize your work. So now we do have to continue because there are still some instructions that we haven't followed through on, right? This instruction says take the derivative. So to this one here. So we need to go further and say, well, the derivative of x to the 7th is 7x to the 6th. We still have the natural log of x cubed plus 2 right there. And then the derivative of the natural log of some stuff, oh, we're going to need to use the chain. So the derivative of natural log of some stuff is going to be 1 over the stuff times the derivative of that stuff, which in this case is 3x squared. Could you simplify this? Sure. You can totally rewrite this part as 3x to the 9th over x cubed plus 2. Not required, but it is good to see how we simplify things if we need to. X to the 7th times 3x squared is 3x to the 9th, and that would end up in the numerator of this fraction. All right, moving on to trig. So really all we're doing here is we're looking at more complicated examples of things involving all the rules we just talked about. So we should be comfortable taking the derivative of anything we listed there. Logarithms, any trig function, algebraic things, meaning x to a power, and exponential things. And then having chain rule versions of them or having them mixed up in a product or a quotient or whatever. So let's incorporate the trig now. So let's say we want to find the derivative of, sure, I like problems like this. X to the 4th times cosine of 6x. So again, it's looking like I'm going to need to use what rule? Product rule. And also I'm going to have to use the chain rule in one of those products. Why don't you all try finding the derivative of this using the product rule? All right, let's take a look and see what we got here. So I'm not going to write out the long way this time. I'm just going to take it. So I know it's going to be the derivative of the first piece, which is 4x cubed times the not derivative of the second piece, or we leave the second piece alone, plus, then we leave the first thing alone, we multiply by the derivative of the second thing, the derivative of cosine of x. Notice how I'm not even thinking cosine of 6. I know the derivative of cosine of x is negative sine of x. So the derivative of cosine of some stuff is negative sine of that stuff times the derivative of the inside stuff. I do think you need to write parentheses around this if you're going to write the minus sign there. Otherwise, it looks like you have like x to the 4th minus sine of 6x times 6. And really, I would definitely rewrite this as 4x cubed times cosine of 6x minus 6 times x to the 4th times sine of 6x. Just to make it look a tiny bit nicer. Often if we have constants at the end, or a minus sign, which I guess is also a constant, we usually pull those out in front of the expression. There's kind of a natural order of like which kind of things you write first. Like usually you write x to a power, then you would write like a sine or a log or an like it just kind of, that's the way it goes usually. Let's do some more. Let's look at, say, sure. Yeah, totally, yeah. Anyone needs a paper, I got. No, I need a paper. If you need more, I got more. So let's say we want to find derivative of secant of sine of x. Cool. Looks like a chain rule to me. So I would encourage you when you're reading math to really, really heavily use the word of. I know it's another syllable and you might prefer to read this as secant sine x, but really take the extra half of breath to say secant of sine of x, because that word of tells your brain that you have a composition of functions and that you know you're going to have to use the chain rule if you're taking a derivative. And if it's integration, it means you might see more easily what you might end up choosing for a u substitution. So really read those ofs. It's kind of the most important word in math, honestly, is the word of. So I remember that the derivative of secant of x is secant of x times tangent of x. So the derivative of secant of some stuff is going to be, and this one's kind of weird, secant of your stuff times tangent of your stuff. Your stuff does show up twice when you take the derivative of secant of some stuff or cosecant of some stuff. It's a little weird, but it happens. Okay, but then what do I still need to multiply by? Right. You guys are pros. Derivative of the stuff. Okay. There's another one here. Let's see. Yeah, sure. What if I wanted to find the derivative of, I'm trying to get through it. Let's see. Let's try, sure. Oh, that's a good one. Where'd you go? Yeah, let's do that. Let's do cotangent to the fourth power of, this is gonna be gross, cosecant of x plus 3x squared. So this one is a little extra challenging because it's written in kind of a not super easy way to see what's happening. Usually when I'm looking at these chain rule types of questions, I'm trying to identify what's the outermost function. What's your thing you're taking the derivative of first and then leaving the insides alone and then multiplying by the derivative inside. In this previous problem, it was clear that secant was the outer function and sine of x was the inner function. So if you're thinking about actually the order of operations here, if you're like doing something to x, first a sine would get applied to x, and then you get secant of that. So sine is the first function that gets applied here, secant is the last one that gets applied here. We kind of read from the inside out. Here, it might not be super obvious, but cotangent is not the last function that gets applied here. So this abbreviated notation, cotangent to the fourth, I would really recommend rewriting as cotangent of cosecant of x plus 3x squared, all raised to the fourth power. And now it might be a little bit more clear that the last thing that happens, the outermost function, is actually being raised to the fourth power. So we have some stuff to the fourth power. What's the derivative of x to the fourth? Right. So what's the derivative of some stuff to the fourth? And then we're going to multiply by the derivative of the stuff. So here we're going to get cotangent of cosecant of x plus 3x squared. And now we have to multiply by the derivative of, drumroll please, cotangent of some new stuff. So what's the derivative of cotangent of x? Negative cosecant squared. So it's going to be times negative cosecant squared of our new stuff, which is also a cosecant in there, kind of weird. Cosecant of x plus 3x squared. But we said the word new stuff, so we have to multiply by the derivative of our new stuff, which is going to be the derivative of cosecant of x plus 3x squared is negative cosecant of x times cotangent of x plus 6x. Whew. Kind of gross. I'm reminding you all that the derivative of arctangent is 1 over 1 plus x squared. I know I should be more careful with my words. The derivative of the arctangent of x is 1 over 1 plus x squared. So now I want you all to try finding the following. The derivative of the arctangent of x cubed times natural log of x. Don't worry about simplifying your answer. Just use the rules we've been talking about. Or as you should be reading this, the derivative of the arctangent of some stuff. Yeah, I can do it.
Thinking of being already.
Correct.
Okay.
Because you're not taking the derivative of the arctangent of x, which is 1 over 1 plus x squared. You're taking the derivative of the arctangent of some stuff.
Okay.
So it
So
should be,
one bar
right, so you should really be getting 1 over 1 plus
of the stuff.
the stuff. So in fact, let's go ahead and talk about that. So if we're taking the derivative of the arctangent of x cubed times natural log of x, we're going to get 1 over 1 plus x cubed times natural log of x squared. And then we're going to have to multiply by the derivative of the x cubed times natural log of x, which is going to necessitate the product rule. So the derivative of x cubed is 3x squared times leave natural log of x alone plus x cubed times the derivative of the natural log of x, which is 1 over x. And I would leave it, so here's a good rule of thumb, and I know you're not doing a lot of derivatives in your calc class currently because, well, it's not on an exam, right? But like if this was an exam question, you shouldn't simplify it unless I say to simplify it. Just like if you're doing an integral, specifically, actually either way, indefinite or definite, if they ask you to find an antiderivative and they say not to simplify or they don't say to simplify, then leave it unsimplified. Similarly, if you're finding a definite integral and you find the antiderivative and you plug in your points, don't spend the time like simplifying that expression to some nice number. Leave it as something gross minus something gross. And if you have time at the end of your exam, then go back and actually try to simplify that. But that's not where you're getting all the points on your exam. Simplifying those definite intervals into nice numbers is not worth a large portion of the points. But if you want to simplify this, I'll point out the x cubed times 1 over x would simplify to x squared. And so you could rewrite this as a numerator of 3x squared times natural log of x plus x squared over a denominator of 1 plus. I probably wouldn't multiply this out. Like you could write this as x to the 6th times natural log of x quantity squared. I don't think that's worthwhile. I would probably just leave it as x cubed times natural log of x squared. All right, one more type of function we haven't gotten to yet, the e to the x's, which come up a lot. Let's say that we want to find, I've actually stuck with the numbers, how shocking. Let's say we want to find the derivative. So I should probably, let me actually do this different way. Let's say I want to find the derivative of e to the x cubed. So sometimes I'm almost always going to write the derivative of something as d dx because that's just the fastest way to write. But sometimes you're going to be like, they're going to give you a function and say, find f prime of x. Well, e to the x cubed is always, or e to the something always feels a little weird because the derivative of e to the x is just e to the x. So the derivative of e to the stuff, you're always going to get back the e to the stuff. And then you're going to have to multiply by everybody. Cool. Just 3x squared. And just because we can say it, I want to point out what this also means for you is that if you were integrating 3x squared times e to the x cubed, the integral of that or the antiderivative of that would just be e to the x cubed plus c. Now, it's not super obvious if you just start with that. If you were just starting with that, you would do a u sub. You'd say, oh, I'm integrating this. I'm going to pick u equal to x cubed for the usual reasons. For the usual, that's not great. If I pick u equal to x cubed, I'm very pleased with this choice because my derivative of u, du dx, is 3x squared. And so my du is exactly equal to 3x squared dx. So I can totally rewrite my integral as the integral of e to the x cubed times 3x squared dx, and then my 3x squared dx is exactly equal to du. This is exactly equal to e to the u. Here's the part where I feel like people struggle with an e to the u substitution specifically, is this integral is going to be equal to the integral of e to the u. And then you have to do one more thing. Actually, two more things. But the next thing we do feels like we didn't do anything. What's the antiderivative of e to the u? Right, e to the u. But watch for a second. We actually need to write that this is equal to e to the u without the integral symbol. Right? This symbol says find the antiderivative of e to the u with respect to the variable u. And then we did it. We no longer write the instructions to say to do the thing that we just did. So when you look at this, that symbol there and that symbol there are just instructions that say find the antiderivative. And then we did it, so we no longer write them. And then since it's an indefinite integral, we need to tack on a plus c. And also, since it's an indefinite integral, and again, I'll remind you, what I'm saying the word indefinite because I don't have any limits of integration. Right? Indefinite integrals are all, so we use the word integral and antiderivative pretty interchangeably, but really what I should say is an indefinite integral like this and an antiderivative are essentially the same thing. Whereas a definite integral where we find the area under the curve, that's where we use the antiderivative and then we plug in some numbers to find the area. And that's why we use this symbol to represent that, because they're so related to each other. So here we're going to finish off by saying we get e to the x cubed. Let's see. With enough practice, you can look at something like this and be like, oh yeah, I know the derivative of e to the x cubed is e to the x cubed times 3x squared. So I know that the antiderivative of this has to be e to the x cubed. In a similar way, I bet you could all make a pretty good guess about what the integral of 2x times e to the x squared is going to be. Why don't you all make a guess right now on your paper? Don't do a U sub, just make your best guess. All right, I'm hopeful that everybody came to the guess of e to the x squared. Because the derivative of e to the x squared is exactly e to the x squared times 2x. And then plus c, because yeah, plus c. Right, some integrals are easy enough that even though you would do a u sub to do it, you can kind of see how the u sub is going to work out. So it's good to practice. What else did I want to do here? Let's see here. There's something else I want to say about e to the sub specifically. Let's see here. So let me kind of throw it all together and get all sorts of bizarre looking things you want to take derivatives of. Like, for example, I could find, oh yeah, we'll do that next. I could say, I'm trying to do this differently. I could say y equals e to the sine of x times the natural log of x squared plus 1. Be really, really unhappy about having to find the derivative of that. It's not impossible. It just requires being diligent about keeping track of everything. So I see a product rule kind of at the first step. I see some function of x times some function of x. And I know that if I want to find the derivative, it's going to be equal to the derivative of f of x times my g of x left alone plus my f of x left alone times the derivative of my g of x. We don't need to write that out, but it might help us see it. So the derivative of e to the sine x, well, the derivative of e to the stuff is e to the stuff times, yeah, which is cosine of x. G of x we're leaving alone, so it's times the natural log of x squared plus 1. Plus, then we reverse it. We leave the function f of x alone, e to the sine x, sine of x, really, I should say. And then the derivative of g of x, well, the derivative of natural log of x squared plus 1 is 1 over the stuff times the derivative of the stuff. And I really, really would not take the time to simplify that. Let's contrast this with the following. Let's say my next function was, I want to find for f of x equal to, yeah, e to the x cubed times secant of x. I want to find the derivative of that. So in this first one, I kind of had the product rule part happening first. In the second one, the chain rule part's happening first. Right? I'm taking the derivative of e to the stuff, and then the stuff happens to be a product, which when I multiply by the derivative of the stuff, then I will have to use the product rule. So my derivative here, the derivative of e to the something is e to the same something times the derivative of that something. But the derivative of x cubed times secant, that's where we're going to have to use the product rule. So I'm going to do the derivative of x cubed. And I want you all to finish the rest. Okay. Hopefully, for the rest of this, so we had the derivative of x cubed, and then we're just multiplying by secant of x. Plus, then we switch it. We leave x cubed alone. We multiply by the derivative of secant of x, which is secant of x times tangent of x. Cool. Let's do one more. I have one more thing in mind. So if you happen to have a slightly different base, like if I want to find the derivative of 8 to the power of 8 to the power of what? Oh, sure. Let's throw some. Oh yeah, let's do 8 to the power of x to the 4th plus the arctangent of x. That's actually not that bad. Okay. Here's something you should be aware of. Whenever you're differentiating an exponential function, like e to the something, or 2 to the something, or any constant base to the variable. If you want more paper, I got more paper. Or you just, sorry. Oh, okay, sorry. I thought you were like, I thought you were trying to like make your paper do more for you. Yeah. Okay. So whenever you're differentiating an exponential function like this, it's always going to come back unadulterated. So whenever you differentiate something to a power like 8 to the something, you're definitely going to get 8 to the same something. Thank you for coming, Carolina. Oh, so before you go, I do have 2 more handouts. So for everybody, actually. So I have a derivative worksheet, which has lots of derivatives on it, and then answers on the back. Not solutions, but answers. So if you want more practice, this is more practice. And then I also have some antiderivative rules. It says Co-21B, you don't worry about that. Okay. I did say ignore the ones that you don't need to know about. So and everyone else can have one as well.
Thank you.
Oh, so I definitely recommend if you're looking for more derivative practice, you can do any of the problems on this derivative worksheet on the first side, and then you can look on the back to see what the answer is. Now, the only thing you have to be aware of is the answer on the back might be more simplified than you have simplified your answer, so you might have to do a little bit of work to make sure that they actually are the same. Or you can ask me to look. Sorry, we didn't finish this one though. The derivative of 8 to the stuff is going to be 8 to the stuff times the derivative of the stuff, which is 4x cubed plus the derivative of arctangent is 1 over 1 plus x squared. And what else do I need to multiply by? Since my base wasn't e. Natural log of my base. Right, man, I know it's been a minute, but remember the rule back here? The derivative of 5 to the x was 5 to the x times natural log of 5. So the derivative of 8 to the x would be 8 to the x times natural log of 8. And the derivative of 8 to the stuff is 8 to the stuff times the derivative of the stuff times the natural log of 8. Okay. So that's a pretty good refresher on derivatives. The other thing I'd like to mention, because I do think it's highly related and somewhat challenging, is how this all plays a role in the fundamental theorem of calculus part 1. So if I gave you this function, say g of x equal to the integral from -1 to x of, what do I want to pick here? Sure. 3t squared plus, sure, secant squared of t, dt. And I ask you to find the derivative. So I can either write it like this, or, so sometimes I'll write it like this, sometimes I'll write it like this. The derivative of the integral from -1 to x of 3t squared plus secant squared of t, dt. The desire here, the want, the reason we're doing this is because we don't want to do all the work that maybe one could do. The whole point of the fundamental theorem of calculus part 1 is that the derivative of the antiderivative gets you back the function you started with. So the short, fast way that your teacher wants you to do this is just to say, oh, the derivative of this function of the the derivative of the antiderivative of this function is just going to be 3x squared plus secant squared of x. End of story. Now, it's a little more challenging if we make a slightly different function and say, oh, actually, that's an interesting idea, James. Interesting.
So if x was on the bottom, we would have a negative.
Correct. Yep.
Does that negative carry out in the end? So like.
Yes.
It's gotta be negative.
It'd be negative parentheses, all of that. So let me point something out here. So ignore the fact for a second that g of x is equal to this interval. What if I asked you to find the derivative of the composition g of x to the fifth? Just using the chain rule and being fine with leaving things as g prime. So if I do the derivative of the outer function, the derivative of g is g prime. So I'm going to get, hold your horses, hold on to your hats, whatever. G prime of my stuff times what? Right, the derivative of my stuff. Okay, check this out though. G of x to the fifth is equal to the integral from negative, right, if I'm using the same function here, it's the integral from -1 to x to the fifth of 3t squared plus secant squared of t dt. And if I take the derivative of this, well, the derivative of that little symbol there should not be there. The derivative of that should be the derivative of this. It's going to be so good. I can fit it in here. But what I'm going to get is, check this out. So I'm going to get g, I should have finished, sorry, I should have finished this right here first. So look here for a second. G prime of x is 3x squared plus secant squared of x. So g prime of x to the fifth, I'm just going to sub in x to the fifth for each x. That's going to be 3 times x to the fifth squared plus secant squared of x to the fifth. That's my g prime of x to the fifth.
Isn't that similar to the initial right?
It's more similar to the more complicated version of the fundamental difference calculus part one. So hold on for just a sec. Times 5x to the fourth. So I just want to make sure everyone's cool with what I'm saying here. So all I'm saying is, I know that the derivative of g of x is this, g prime of x is that. And then if I use just the normal chain rule for the g of some new stuff, the derivative of g of some stuff is g prime of that stuff times the derivative of that stuff. But then what I'm doing is I'm actually saying, well, I know what g prime is. G prime of x is 3x squared plus secant squared of x. So g prime of x to the fifth is 3 times x to the fifth squared plus secant squared of x to the fifth. I'm still multiplying by the 5x to the fourth at the end, right? That's still, this part here is still right there. But this is the version of the chain rule where you have a more complicated thing up here. And instead of like doing the straightforward thing, we plug in the x to the fifth to each spot, and then multiply by the derivative of x to the fifth. So look, we get the same thing. We get 3 times x to the fifth squared plus secant squared of x to the fifth times the derivative of x to the fifth, which is 5x to the fourth. So this is why when you have a more complicated thing up here, you have to multiply by its derivative at the end. So let me give you another example, and then we can talk a little bit more about this. I know it's 4:30. Let me do one more thing. So if I said, find the derivative of the integral from x to the sixth to 2, let's make it a little bit less terrible. Let's say we had cosine of t plus natural log of t dt. Well, first of all, according to what Arthma? According to what Arthma said, what should we have in front of the whole thing? Because of where the x to the sixth is. A negative. So we know it's gonna be negative. And then we're gonna plug in x to the sixth for each t. So we're gonna get cosine of x to the sixth plus natural log of x to the sixth. And then we have to multiply by what? Exactly. The derivative of the inside, which is our x to the sixth.
Which is lower
In this case, yes. But it's really just whichever limit happens to be the one that's variable.
the variable.
Right. And if you had variables in both of them, if you had to say like take the derivative from the natural log of x to x to the seventh of something like, I'm trying to make things not too terrible here, e to the t plus t to the fifth plus, sure, sine of t, we would exactly get, so first we're going to plug in, which thing first, top or the bottom? Top, always the top first. So we're going to get, it's going to be kind of gnarly, e to the x to the seventh plus x to the seventh to the fifth plus sine of x to the seventh, all multiplied by, I'm not plugging in the bottom yet. I'm using the chain rule and multiplying by the derivative of that. Minus, now we plug in the bottom limit of integration. And we get e to the natural log of x, which yes is just x, but we're not going to change it, plus natural log of x to the fifth, plus sine of natural log of x, all times the 1 over x, the derivative of the natural log of x.
You always multiply it
Multiply what?
by the derivative.
Yeah, I did it here, right? Up here, I took the derivative of the integral from -1 to x to the fifth of this function. I plugged in the x to the fifth, and then at the end of the day, I multiply by 5x to the fourth. Technically, I even did it here. I plugged in x, and then I multiplied by the derivative of x, which is 1. Yeah,
Why was it constant? You don't have to plug it
right, because if you plug it in and then take the derivative of that, you get 0. The constants are inconsequential.
Wait, this only applies when it's a variable, right? Not when you're actually evaluating it with actual.
Right. So again, I want to point out, we are not evaluating the integral, we are taking the derivative of the integral. Now, I will show you, even though you shouldn't do it this way, is that you could do this first one the long way. So here's what I mean. This and this one here. So if I wanted to find this derivative the long way, you are welcome to write this down. You may not want to write this down. If I was going to find this one, oops, come on, papers get in the right spot here. So if I was going to do this one the long way, check this out. So I'm going to say I want to find the derivative of the integral from -1 to x to the fifth of 3t squared plus secant squared of t. And in this particular example, we are technically able to anti-differentiate the inside function. So we're going to get, watch, the derivative of, well, what's the antiderivative of 3t squared? Which is going to be t to the third, because the 3's cancel. What's the antiderivative of secant squared of t? Evaluated between -1 and x to the fifth. So we're going to plug those in. We're going to get the derivative of x to the fifth cubed plus tangent of x to the fifth minus -1 cubed plus tangent of -1. And now we're going to take the derivative using the chain rule quite a bit. So let me ask you, what's the derivative of some stuff cubed? 3 times my stuff times, right, times the derivative of the stuff. Plus, what's the derivative of tangent of some stuff? Times minus, what's the derivative of -1 cubed? What's -1 cubed equal to? -1. What's the derivative of -1? 0. -1 is a, and its derivative is. Okay, how about tangent of -1? Let me ask you a different question. Is tangent of -1 a constant? Yeah, I don't know what it is, but it's not changing. So the question you have to ask yourself, if you're asking yourself, is this thing a constant? The question you're really asking yourself is the variable x somewhere in there? So when I write tangent of -1, is there anywhere for the variable x to be hiding? No. So tangent of -1, plug it into your calculator, it's going to be, I don't know, probably close to -1 actually. But the derivative of that constant is also 0. Which is why the constant part doesn't matter. But now look, if I factor out the 5x to the 4th, this is exactly 3 times x to the 5th squared plus secant squared of x to the 5th, all times 5x to the 4th, which we could have just achieved by plugging in x to the 5th for each t, and then multiplying the whole shebang by the derivative of x to the 5th, which is what we should do. Okay, it's 4:37, I should probably stop.